In these 3.2 notes, we're going to look at factoring a polynomial using greatest common factor, GCF, and grouping. So these are two methods that you can use to factor a polynomial, potentially. So remember, to factor something is to rewrite the expression as a product of its prime factors. And this can be numbers or expressions. So a GCF, which again is the greatest common factor, is the highest number or term that will divide into two or more terms evenly. And if we have powers in our expressions, the GCF of a variable or a power is the smallest exponent of the common variable. Let me explain what that means. So for example, here we've got 12a squared b and 18a cubed b squared. So first, let's consider the numbers, coefficients here. We have 12 and 18. Well, the greatest common factor between these two numbers, the biggest number that goes into both 12 and 18, is 6. 6 goes into 12 2 times, and it goes into 18 3 times. Now we look at the powers. So you've got a squared and a cubed. Well, we want the smallest exponent of the common variable. So we can take out an a squared from both of those. So a to the second power is our GCF there. And between b and b squared, we can just take out a b. b is our GCF of that. So the total altogether GCF of those two expressions is GA squared B. Sorry, 6A squared B. Okay, so let's practice this a few more times. We're going to find the GCF of the following sets of expressions. Some of these are just numbers. Some of them are expressions with powers, so we can do both. Okay, A, between 18 and 36, 18 is our GCF. If you're not sure, you can do a factor tree or hedging, where if you take both numbers, so we can take 18 and 36 here, and we can divide them by prime numbers. So we can divide them both by 3, and we get 6 and 12. We can keep going, divide them both by 3 again. We get 2 and 4. We can divide those both by 2, get 1 and 2. Then we're done because we reached 1 here. So now if you multiply together the numbers they have in common, they both have a 3, and a 2. This one also has a 3, and a 2. So if you multiply a 3 and a 3 and a 2 together, you get 18, which is the GCF there. So that's just a little refresher on how to find the GCF. If you're not sure, you can use a factor tree or hedging, so you can find the common factors they have. Alternatively, if you divide 36 by 2, you get 18. So that's another big clue there. All right, we have 18, 30, and 54. The GCF here is going to be 6. Something else you can consider after you find the GCF is if you just double check, divide each number by that GCF. 18 divided by 6 is 3, 30 divided by 6 is 5, and 54 divided by 6 is 9. Those three numbers don't have a common factor other than 1. Because 3 and 5 are prime, we don't have any more common factors to take into consideration here. So 6 is the greatest common factor. Next problem, we have 12an squared and 40a to the 4th. So again, first consider 12 and 40. I believe this is just 4 for the GCF. And if you double check that, 12 divided by 4 is 3, 40 divided by 4 is 10. Those two numbers don't have any common factors other than 1, so we're good there. And then we have to find with the powers. Now the only variable they have in common is the a, and the smallest exponent present on a is a 1, So 4a is our GCF here, 4a to the first power. All right, for example D, we've got three numbers to consider, 14, 20, and 35. Well, if we think about this, 14 is just 2 times 7. 20 is 2 times 10, so 2 so far, but 35 is not even. These three numbers don't have a GCF other than 1. And if we doubly make sure with a little hedging, we can divide this by 2, we get 7. Those are both prime. 2, we get 10, which we can divide into 2 and 5. And 35 is 5 and 7. So these three numbers don't have a GCF other than 1 because they're all a different combination of prime factors. So 1 is our GCF for the coefficients. Then we want to look at what variables they have in common. So we have a squared, and a. So that's just an a to the first power is our common power there. B to the third, b to the third, b to the third. They all have a b to the third in common. And only the last one has a c, so c won't show up in our answer. So just 1ab to the third or ab to the third without the 1. If you like that better. So there we have our GCF there. So now we can use this to factor an expression. So what we want to do is think of it as reversing the distributive property and divide each term by a GCF. So if you look at example A, we have 6x plus 18. The GCF of 6x and 18 is 6. And if I take that 6 and divide each term by it, I get 6 times x plus 3. And so I've rewritten this expression as a product of its prime factors, 6 and x plus 3. So you can divide out a GCF and you have this expression right here. For example B, we can take out an x. 2x squared and x just have an x in common. I can divide them each by x. I get 2x plus 1. For example C, 3x squared plus 15x. Well, the GCF of 3 and 15 is 3, and the GCF of x squared and x is x. So I can divide both of those terms by 3x, which leaves me with x plus 5. And lastly, I have 2x cubed minus x squared plus x. Those all three just have an x in common. So if I divide all those by x, and if you remember, dividing by a variable, you just subtract 1 from the exponent. So this first term gives me 2x squared. The second term is just x minus x, and then x divided by x is 1. So there we have those four terms divided by their GCFs. Now we can take this one step further and do what's called grouping, which is taking a GCF of a pair of terms. And it's always important and helpful to look for an overall GCF first. So if we look at example A here, these four terms do not have a common GCF. Your big tell here is the fact that they don't all have x, they don't all have z, and 9 and 4 don't have a GCF in common. So we can go straight to grouping. And the way we group is to consider these in pairs. So if I first want to take the GCF of the first two here, 6x squared y and 9xyz, they have a GCF of 3xy. And what's left over is 2x plus 3z. And now for our second set, we can take out a 2. So plus positive 2. And what's left over is 2x plus 3z. Now notice, if you do this correctly, the two factors that are in parentheses should be the same. So what I can do is take that out, 2x plus 3z, and then what's left over are the terms outside. So then we have a 3xy plus 2. And that is the factored form of that 4-term polynomial there. So it really is just reversing the distributive property. If I were to multiply this expression back together, I would do 2x times 3xy and 2x times 2, and then I'd multiply it like this. And I would end up with this same middle step before I combine like terms and get the original one. So we are just reversing the distributive property. It just seems like a complicated process. So on example B, again, look for an overall GCF. It just makes it easier. It won't make it impossible if you don't. If you miss the overall GCF, it'll be okay, but it's typically easier if you do. These all have a GCF of 2. They're all even, so I can take a 2 out at least. This one is just 2, so my initial overall GCF is 2. That leaves xy minus 4y plus 3x minus 12. Okay, and then I can do grouping. Take out a GCF from each pair. So from the first one, I can take out a y. That leaves x minus 4. And from the second pair, I can take out a 3, positive 3, which leaves x minus 4. And that's what I wanted, right? I have x minus 4 in both parentheses. They are the same. So for my final answer, I have the 2 I pulled out from the beginning. I have the x minus 4 in parentheses, and then the y plus 3, those GCFs that I took out from each pair. Okay, example C. Again, look for an overall GCF. I don't believe they have one. So we can go to grouping. And if you miss the overall GCF, it'll show up when you do grouping. So if you miss it at the beginning, it will show up in one of your factors. For example, on B, if I didn't take that 2 out, I might have gotten a 2x minus 8 or a 2y plus 6. And I could have taken the 2 out afterwards. So here, I can take out a 2x from the first pair, leaving a plus 3c. And then I can take out a b, leaving a plus 3c. And now I can write my final answer. I have the a plus 3c's that are in parentheses, and then the 2x plus b left over. Final example here. Let's just go straight to it. From the first 2, I can take out a 2m, which leaves 3x plus 2. And now see how these are both negative? I can take out a negative term. So I'll take out a negative r from each of them, which will leave 3x plus 2. Typically, you only want to do that if they are both negative, or if you need to make it match the other term in parentheses. So our final answer here is 3x plus 2 and 2m minus r. So grouping is a little more complicated, but at its core, it is just using a GCF to factor out a 4-term polynomial.